Alright, welcome back to our slides on logic. We were down here starting to talk about predicates, which is like a function on propositions. So like you give it two things and then eventually it becomes something that could be true or false. So you have to like plug in me and cats in order to get something that's true and some other stuff to get false. It's not yet false or true because you still have things to plug in, they're variables. So with that, let's start talking about quantifiers, because that's where we're going with predicates. They give us the ability to say stuff like this. So once you make a predicate, you can say like p of x is true for every x, no matter what x is. And the fancy computer science / mathematics term that we use to kind of mean both of these sentences, the words that we've chosen in mathematics is for all. So we say that p of x is true for all x. We'd like to say that, all right? No matter the x, for this predicate, it's always true, all right? So we introduce a fun symbol to mean for all because we say it so much. It's an upside down A. It's like an A that's been flipped around to 180. And like here's an example of using the for all quantifier, all right? So let's define a predicate. Let's say that p of x is Lawton loves x, all right? So could be true or could be false depending on x. And let's say that the domain of p, because every predicate has a domain, usually it's specified. Let's say that the domain of p is all cats, and so obviously for all x, p of x is true. Does that make sense to you? Do you see how I'm reading that? So for all x, no matter the cat, I love it. See how you can plug in every cat in the universe, and that's how it works. It's always true. So x ranges over every cat is what we say, and it gives us the ability to take a predicate that hasn't been applied to anything yet and apply it to everything all at once and then get something that we can prove true or false. So it's a very powerful idea, the idea of a quantifier. This is the universal quantifier. That's the for all. All right. One special thing that it does that I want you to remember is that every quantifier, including this one, introduces a new variable because we need a variable to range over in the predicate that we're going to apply it to. All right. So it introduces a new variable, so you can use it in the rest of your statement. Don't forget about that. And the variable name doesn't matter. It's just like a placeholder. So I could have said just as equally for all y, p of y is true. For all z, p of z is true. It's like y is every cat now. Z is every cat now. It doesn't matter. It's just a variable. It's just a placeholder. And so those are equivalent statements. This is just as true as this is. Okay? So that's your universal quantifier. Let's talk about the other very popular one. It's called the existential quantifier. All right, it's a little bit of the opposite. So it's for when you don't want to commit. You have a predicate. You just want to say that it's true sometimes for at least one value. All right, this is what we want to express. P of x is true sometimes for at least one value, and the fancy mathematical term we use, or the phrase, is there exists. So we say that there exists in x such that p of x is true. That's what we turn our statement into. And so because we say there exists so much in logic, we made a new symbol for that as well. We have the 180 flipped E, so it's like a backwards E. You read that as there exists. All right, so again, let's come up with an example predicate. Let's say p of x is Lawton owns an x, right? So some things I own, some things I don't own. This isn't always true. And let's say that the domain of p is all cars, all right? So I only have one car. I don't own every car in the universe. So it's not true that for all x, p of x is true, right? Does that make sense? I don't own every car, because that's what that would mean. But it is true that there exists an x such that p of x is true. There is some car that I own. Do you see how that's shorthand for that? That's the idea. So please yell at me if this does not make enough sense, but that's where we're going. And this is trying to say that I own just one car. There's one way to prove this true, not every car. X is filling in for at least one thing, not everything, okay? So again, it introduces a new variable. It gives the idea of like it takes this predicate and it turns it into something that you can prove true or false. You're kind of losing some information because you're like, I just know that some car is what I own. You haven't like given me the license plate number or anything. It does introduce a new variable though, so that you can use it in the rest of your statement all over again. So there is some x such that p of x is true, and that x happens to be my car, all right? Whatever it is. And the variable name, again, doesn't matter. It could be there exists a y, p of y is true. There exists a z, p of z is true. Claiming all that is the exact same idea. So with that in mind, here's a question for you. You try this. Let me define two predicates. Here's p of x and q of x. All right. And the domain, let's pretend that the domain of each of these predicates is the set of students in the class. So you can plug in a student for these x variables, and it could either be true or false. So p of x, let's define that to mean that x was born in September. All right. So if p of x is true on a student, that means they were born in September. And then let's define q of x to be that x is at least 20 years old. All right. So if you plug in the student x, of course, some students in this class are under that. Some students are at least that. So it's sometimes true, sometimes false, given an x, not yet true or false. All right. So here are two questions involving quantifiers. So try them both. Do you think that it's true that for all x, p of x is true? Try to translate this back to English. That will help. Yes or no. And then also this one. There exists a z such that not q of z. All right. Or another way to say this is q of z is false. So think about both of those, pause the video, and then we'll come back and I'll show you my answers. All right, for A, is it true that for all x, p of x is true? So what does this mean in English, first of all? Let's translate this to English. That's saying that, like, all right, if x was born in September, we're saying that every x was born in September, so every student, everybody in the class was born in September. That's what it's trying to say. Everybody, do you see how I'm reading that? Was born in September. That's the idea. And do you think that's true for everyone in the class now that you've seen that translated to English? No, that's a false statement. All right, so that answer would be B. And then how about this one? There exists a z such that not q of z. That whole thing is true. All right, we're claiming that. What does that mean? How do you translate this to English? There exists a variable, so that means it's filling in for q's parameter. So that's going to be a student. There exists a student, call them z, such that not q is true for that student. So q is false for them, all right? So that's saying that, all right, for somebody, call them z, z is not at least 20 years old. So they're like under 20. You see how I'm reading that? So there's a student that's trying to claim that there's a student under 20 in this class. And I'm pretty sure that's true. So it's not true for every student, but it's true for at least one, I believe. And so I would say that the answer is A for that. All right, so that's examples of the universal quantifier and the existential quantifier. And so remember that they're introducing variables. So let's go back here and I'll rewrite this. So when you have the universal quantifier, you say for all some variable, and that after you say that introduce your variables like you declared it, now y can appear here for the rest of the time that you're trying to say something. Y can appear here. That's the idea. And then same for existential quantifier. You say there exists some z, and then you can talk about z for the rest of your argument. Now z can appear here. If only I could write appear. And then, let's see, what else did I want to say on this slide? And remember that you can swap out the variables as long as you're consistent. It's just like whatever one you introduce, you got to use that one. And it's all equivalent. All right, so hopefully those answers make sense. Please yell at me if they do not. And let's try the next one. All right, so here's a new idea. So let's say that the domain of these predicates P and Q that I'm about to define are just A, B, and C, whatever A, B, and C are. Maybe they're people. All right, so there's only three things that P and Q are either true or false for, so we can make a table for that. So we say that, all right, P of A is true. P of B is false. P of C is true. So it's kind of easy to just read it off. So if those are the only things that are in the domain of P and Q, it shouldn't be too hard to figure both of these out. So try A and B. Is it true that for all x, not P of x is true? Is it true that there exists a y such that not Q of y is true? Or, equivalently, there exists a y such that Q of y is false? That's another way you can read that using a negation. So give those both a try. And now, assuming that you tried them, let's do it together. All right. So the first thing, hopefully you've noticed, is that for all is kind of saying something for everything in the domain, and so it's like you gotta run it on A, B, and C. Try every single possibility. All right. So is this true? Is it true that not x, for all x, not P of x is true? That's trying to claim that for A, B, and C, P of x is false for all of them. You see that? It's trying to claim like a bunch of ands. So here's the key idea for all. key idea. And sometimes your domain is infinite, but this is still a good thing to think about. So when you have a for all, it's just a bunch of ands. If you don't see that, let me show it to you. So like this is trying to claim that, all right, for all x, not p of x is true. So that means it's trying to claim that not p of a is true, and not p of b is true for everything in this domain. Not p of b is true, and it's trying to claim that not p of c is true. Is that true? Sorry, I say true and false way too much in these slides, but that's the breaks of talking about logic. So is it true that not p of a is true? So is p of a false? No. So this is immediately, like this becomes false, and so the whole thing becomes false. The only thing for which not p of something is true is this one. Not p of b, yes, that is a true statement, because p of b is false. But the rest of these, not true. So equivalent, you got to have everything true to make an and true, so it's false. Right? It's very hard to prove a for all, because you got to try everything. It's a bit easier to do with there exists, right? So the key idea for there exists, hopefully you see it's kind of the opposite now, because it's just a bunch of ors. There exists is just a bunch of ors. So this is trying to claim, like, is there a y such that not q of y is true? So it's like, all right, try q of a. Is that not true? Try q of b. Is that false? Try q of c. Is the negation of that true? So it's trying to claim this. It's trying to say, all right, is not q of a true? Or maybe I could use b as my witness to this being a true statement. Is not q of b true? Or is not q of c true? Any one of those? And so this is a true statement. This is equivalent to true because we have at least one of these guys that's false, right? Not q of c is a true statement. This whole thing right here. Because q of c is false, the negation of that's true. And so that this whole thing becomes true even though both of these are contributing falseness, right? This is true because not q of c is a true statement, all right? So that's how I want you to think about them. Even if you have an infinite domain, it's really just a bunch of ands for all, and it's a bunch of ors for there exists. You just got to find one good one, and then it makes it all true. But for all, you gotta make sure they're all true at once. Okay, it's a bit harder. So again, yeah, the way I'm reading this is like p of a is true here, and then like q of b is also true. That's how you read this table. All right. So hopefully that's making a little bit of sense in your brain. And we're ready to learn about more new things. All right, so when you have a quantified statement, I kind of told you here that for all and there exists are kind of their opposites. This goes farther than even what we've said. So De Morgan's law is a thing, right? Because a for all is a bunch of ands and a there exists is a bunch of ors, and they get flipped when you push a negation inwards. So you can do that for a for all and a there exists. You can push a negation inside of each of them. So like when you have this, you can change it. You can change it and you can flip it, and it will turn into a there exists for reasons that we just discussed. All right. So what is this trying to say? It's trying to say that it's not true that for all of x p of x, which is a disgusting way to say all this. It's very very vague, but that's what it's saying. It's not true that for all of x p of x. So what does that mean if you just think about that? How can you restate that in an easier to understand way? So it's not true that for all of x p of x is true. That's trying to say that, I mean, they're not all true, so there must be one. There must be one that's like ruining the party, right? There must be one element of the domain where p of x isn't true. Do you see how that's an equivalent idea? So that means that the negation of this whole thing, the negation of for all x p of x, you can push that inwards and it becomes this. It's like, all right, there exists in x someone that's ruining the party such that not p of x is true. That's the reason this whole thing was false. All right, there's at least one that was ruining everything. All right, so the for all gets flipped to there exists because at the end of the day it is just a bunch of ands turning into ors and you're doing De Morgan's law. All right. And then the negation gets pushed inwards to be next to everything that was inside of that quantified statement. Okay? So that's a cool little idea. So you can push negations over quantifiers, and that makes it easier to think about and probably easier to prove. All right? Let's do this one because it's the idea that's the exact opposite. So it's not true that there exists an x such that q of x is true. Right? think about that long and hard. What does that mean? What's another way to restate that? Another way to say it? That means that, all right, if it's not true that there exists an x such that q of x is true, that means that they all must be false. You see, I've turned something that, excuse me, I've turned something that has a there exists quantifier into something talking about every element of the domain. So that means q of x is false for every element of that domain. And so therefore, this is equivalent to for all x, not q of x. We pushed it inwards. Boop. And so the there exists gets turned into a for all because we're essentially doing De Morgan's law on potentially infinitely many things, and we've pushed that negation inside. Okay? Isn't that fun? So we always like to do that because I think you've seen already, hopefully in your homework, that like this leads to something that's easier to prove or prove equivalent to other things. So that's why we want to do it, and hopefully you can see the logic behind it. So with that, now we have all these tools. Let's talk about actually proving things. Like I give you this statement, and like we're using real math rather than tables of things. Like how would you go to prove a for all quantified statement or a there exists quantified statement? All right. I want you to think of it like a fight, like you're fighting somebody. Okay. So when you have a for all and you're trying to prove a for all, like for all x p of x, what you need to do is imagine, like, because you got to try every element of the domain. Imagine that like it's your worst enemy that's getting to pick the value of that variable because they're really trying hard to make it false and make your life horrible. All right, they're trying to make that predicate false, but it's your job to like beat them up and prove that no matter what, even for that horrible value of x, it's still true. All right, so to prove this, like you got to prove that p of x is true, even if x is like the hardest thing in the domain. You got to show that it still works, all right? Because that's, of course, the one that your enemy's going to pick. And you got to beat them up and bash it down, all right? Make sure that that's still true. So that's like a for all. Think of it like your worst enemy gets to pick that variable value. So that's like hard. And then with a there exists, it's like your turn to throw the punch because you get to pick the special value of that variable that makes the predicate true. It's okay if there's just one. Isn't that nice? So it's a bit easier. So to prove a there exists an x such that p of x is true, you can pick the greatest x in the domain, the easiest one to worry about, because you just got to show that you got one good value that x could be. All right, you get to use your weapon of choice, and your enemy just has to sit there and like get beat up. So there exists is a bit easier, I would say, than for all, if you think about it this way. But that's the idea. Your worst enemy gets to pick for a for all, and then you get to fight back with a there exists. Okay, so that helps my brain at least. So think about it that way, if that helps you too. And with that in mind, let's start to talk about fancier ideas. Like you can prove this, just try every element in the domain. You can prove this, pick a good x. What if you had something with multiple quantifiers? Like one day, I'm going to give you this real soon. Like you have some statement that's saying like, all right, for all x there exists a y such that for all z, there exists a p, ... and then something involving all of those variables at once, all right? So there's an order to it, like for all x, there exists a y, such that for all z, there exists a p. You got to read it from left to right and work your way this way inwards to like get rid of all the variables, okay? So when you have a statement that looks like this and it's disgusting, you have to work from left to right, and that's our custom. And remember that it is a fight, all right? So here's the idea. So if it's a for all, your enemy's picking something horrible, right? The hardest possible thing. And then you get to move to the next quantifier. Like, so if this is the first thing, the first quantified thing, your enemy's picking a horrible value of x, and then it's your job to do the next one, right? If it's a there exists, that's the next thing. It's like your turn to pick your weapon of choice. And like that's your good value for y. It's trying to counter the x, all right? And then for all z, then it's your enemy's turn to fight back, pick a horrible z value, and then if there's a there exist after that, then you get to pick a good p, all right? That's how it's working, all right? So when it's a for all, your enemy picks. When it's a there exists, you get to pick. And you just keep on moving your way inwards, and then you have values of variables to like try out and finally do something with, all right, on the inside. So so the order really matters when they like flip-flop like this, for all and there exists, for all and there exists. if you have a for all and a there exists, it's like you get to throw 2 punches or your enemy gets to throw 2 punches. The order doesn't really matter in that case. Like here's an example of a double for all quantified statement. All right, for all x, for all y, x plus y is less than or equal to x, or x plus y is greater than or equal to x. All right, so translated to English, do you see how I'm trying to say that? For every x and y at the same time, like either this is true or this is true. You don't have to really worry about what's inside. So do you see how this could have just as easily been this guy, like for all y first? It doesn't really matter, right? Because your enemy's picking twice. So for all y and x, or for all x and y, this stuff is true. All right, so the order really, really matters when it goes and they flip-flop. So when it's a for all there exists, or there exists for all. All right, the order almost always matters, and your textbook is going to give you some good examples of that. I have a silly one first, though. Okay, so let's see. Wait, before we get there, let's just put some marks on here for posterity. So I could have flipped these. It doesn't really matter. It's just saying like either this is true about x and y, or this is true about x and y. The order in which your enemy picks those horrible values for x and y does not matter. So like they could have been flipped right here and right here. Okay, it will be an equivalent thing to be proving. All right, but these guys are where you got to watch out. All right, so with that in mind, let's talk about multiple quantifiers, and I'll show you with cats, of course, as an example. So let's define a predicate on 2 variables. Let's say m of x and y. Let's define that to mean that x sent a cat meme to y. So let's say that the domain of x and y are like people. And so hopefully you'll see that for all and there exists, it doesn't matter the order of these things. All right, so if I say this, if I claim that this is true, for all x, for all y, m, x, y is true, do you see how that means everyone sent a cat meme to everyone else? Because like you're quantifying over x and y, everybody, this is true for every possible value of x and y, even like maybe if they're the same, like you can send a cat meme to yourself even. So this is saying that for every person's x and y, m of x, y is true. So like this is always happening. Everybody, every x sent a cat meme to every y, all right? And so the order doesn't matter. It's like you could flip-flop these. It still means everyone and everyone. Does that make sense? So yeah, try to stare at this long enough to have that make sense. And so hopefully you can see how this is translating to this English. That's a key idea. Okay, so there's that one. Sorry for the background noise if you can hear that. We'll get through it together. Also, if you have a double there exists, again, you could flip-flop them and it doesn't matter. Watch. Because what's this trying to say? There exists an x and there exists a y such that mxy. So if you unfold the definition of that predicate, there exists an x and there exists a y such that x sent a cat meme to y. So that's just trying to say that there's some person somewhere. That's like the sender. X is the sender, and y is the receiver. And there's like they're both existentially quantified. So somebody sent a cat meme to somebody. Could have been the same person. We have no guarantee. There's just some x and some y such that this is true about them. All right. It doesn't matter in which order you pick the sender and the receiver. It's just this is the way it happens. Does that make sense? So you could have flip-flopped those. For there exists a y, there exists an x, such that mxy is true. So that is that one. And then these guys, the order really, really matters because if you flip-flop them, it means something completely different. All right, let me show you that. So for all there exists, or there exists for all when they flip-flop, do you see how these both mean different things? So for all x, there exists a y such that mxy is true. That's for all quantifying over the senders. Do you see that? For all quantifying over the senders and existentially quantifying over the receivers. So this is trying to say that everyone, right, because x ranges over everybody, everyone sent a cat meme to somebody. All right, you get to pick a different somebody for each person, but everyone sent a cat meme to someone because that's the order. So for all x, there's somebody. For every sender, there is some receiver that's getting that cat meme. So everybody sent a cat meme to someone. See how that's working out? So that's completely different from this one, where we're existentially quantifying over the senders and universally quantifying over the receivers. So this is saying there exists an x, there is some sender, someone, such that for every y, for every other person, x sent something to y. All right, so someone sent a cat meme to everyone. That x person, that one good one, doesn't matter, it could just be one person, sent a cat meme to everybody because the receivers are being universally quantified. So somebody like sent a chain message or like replied all, and they sent a cat meme to everyone. Okay, does that make sense? The difference between those two. And so when you're proving stuff, the order really, really matters, and I hope you can see that. Okay, so that's what's going on there. And with that in mind, let's have some examples without cat memes. Let's go back to math, because sadly this is a bit of a math class. So here's an example predicate, all right? And let's say that P of xy is defined to be x times y is equal to 1, all right? And let's say that the domain for x and y is every positive number. So nothing negative, no zeros, but it's every positive number. And so you can plug in any positive number for x and any positive number for y and get this, and it's either true or false for them. All right, so let's plug in some values. So, for example, P of 1, 1, that is a true statement, right? Because 1 times 1, 1 for x, 1 for y, 1 times 1 is equal to 1, and that checks out. And then P of, I don't know, 1/2 and 2 is also true, right? Because you multiply them together, you get 1. So I'm using the predicate. So what else? What else? Let's ask this. Is it true that for all x, there exists a y such that P of xy is true? All right. So the idea here is your enemy's picking a value first, and then you have to counter it with a y, because it's your enemy's turn first. They pick an x. They can pick any x in the world, and then it's your job to always find a y such that this is true. All right. So you can pick a different y for each x, because your enemy goes first. Does that make sense? Because you're working your way from left to right. For all x, your enemy picks something. So like they're trying to say P of, I don't know, 1/2. And then it's your job to find a good y to make P of xy true. You can counter and be like, yeah, here you go, 2. Haha, it works. And then let's try another one. Let's say, all right, your enemy picks something horrible. It's like, I don't know, 72/34. So your enemy gets to try every possible value. Do you always have a y to counter it, though, and make this true? You sure do, because you have the inverse. You can just say, all right, I choose as my y for your x 34/72, and now you multiply them together, their inverses, you get 1. So that's not too bad. If you get to go second, like you have like home team advantage. That works out. All right. This one is a bit harder. All right. This one might be false. So this is a true statement, because you can always find a y after your enemy picks a bad x. Okay. To make this true, you can pick the inverse. All right. So this one, we're not going to have an easy time with. Is it true that there exists an x such that for all y, P of xy is true? And remember the order of the fight, we get to throw the first punch because the there exists happens first. So you have to pick one good x that works for every y. There exists an x such that for all y, x times y is equal to 1. See that? So you're picking an x first, and then your enemy can hit it with anything. All right? They can pick some horrible value. So, like, let's say that, all right, I don't know, our one good value is like 24. That's stuck. We're stuck with the value 24. Like, we're fixing that. Fix x equals 24. And now our enemy gets to just bash it with whatever they want. They could be like, all right, we picked 24. Our enemy gets to try any value. They could be like 2. And now it's false. Now it doesn't work. Or, like, your enemy's going to try every value at the end of the day. 24 and 3. There is no value that we could pick first that can be fighting every other one and like end up like getting 1 when we multiply, right? Because your enemy, you know your enemy's not going to pick the inverse. It has to work for every value, okay? So this is trying to say that, like, is there an x such that it's the inverse of every y? That's not true. So this is a false statement, all right? Because we have to pick one x and it has to work for every y. It just doesn't work out. There is no value, there is no number that's the inverse of everything, okay? So, with that in mind, hopefully you can see how this one was easier. We get to throw the second punch. So this is easier. For all there exists is easier than there exists for all, because you have the home team advantage. You get to go second. You get to counter each value of your enemy's thing. Whereas for this one, you got to pick something first, and like it's got to work for everybody, which is a bit harder to do. Okay? So with that, here's a question for you. You try it now. So let's define this predicate P like this. Let's say that the domain of P is every pair of integers. So x is an integer, y is an integer, whole numbers, could be negative, could be 0. P of xy, define that to be x plus y equals 2. All right, so try this. Is it true, or first of all, let's try, let's give some examples. Like, for example, P11 is a true statement, because 1 plus 1 is 2. P of 02 is a true statement, because 0 plus 2 is 2. All right, now try these. Is it true that there exists an x such that for all y, p of xy is true? And is it true that for all x, there exists a y such that p of xy is true? You might have a hard time with one of these and not the other. Okay, so give those both a try, and then we'll have fun with it. So this is the harder one, right? Because you get to go first. You have to pick one good value. You gotta bet your life on all right, my x value is 1, and then it has to work for every y. You see that? Is there some integer that you give another value, for every other number, that plus the number is always equal to 2? No. And your enemy is totally going to come along and they're not going to give 1. They're going to give 42 or something. It has to work for every value that your enemy could possibly give. There is no one good value of x, such that for every other y, the value is 2. It's got to be the inverse of 2, the additive inverse of 2. And so that's just never going to work out. You can't pick one good number. So this is not true. You see that? Do you see how I'm reasoning about that? Do you see how I'm reading it out, translating it to English? That's all the kind of stuff that I want you to get good at. And so your homework's going to help you practice that. And so for this one, this is the easier one, so maybe the answer is yes. So is it true that for all x, there exists a y such that p of xy is true? And so the idea is your enemy's going to pick every possible value. They're going to be I don't know, 0. Is there always a good value to counter with that? They get to pick first. Then you get to go second. Can you counter the 0 with a good value that makes x plus y 2? Yeah, you can pick a 2 there. No matter what your enemy picks, you can just solve the equation x plus y equals 2, because you get to go second. You can pick any new value, a different value for every x. That's beautiful, right? You just solve it. Choose as y whatever 2 minus x was, and then you're good to go. All right. So there's always a counter to your enemy's pick. All right. It's got to work for everybody eventually, and there is always a good one. It's just the solution to this equation. Do you see that? You see how that's easier too? So hopefully these ideas are coming together in your mind. I know we have to go a bit fast. There's a lot going on, a lot of new terms, but hopefully with this, your textbook and your homework, you'll get it. All right. So with that, we are now fluent in logic, right? So we can actually prove things. We can reason with it. These are kind of hand-wavy proofs. They're not mathematicians wouldn't accept what we're saying here. We can't just circle no and not give a real reason. Let's learn how to give those reasons, all right? Let's learn how to prove new things from old things we already know. That's the first step, okay? So here is the idea. So we're usually arguing something. Our proof is we're making an argument. We're claiming that something is true. And an argument, that's a technical term in logic. It's a sequence of propositions, all right? It's first a sequence of propositions called hypotheses. You're assuming all these things. And then at the very end of the day, you have a final proposition that you're trying to claim called your conclusion. All right, so here's kind of what an argument looks like. You have a bunch of hypotheses. I'm very bad at saying that word. So here are your hypotheses. And you're saying assume this and assume this. And then you're trying to say, therefore, Q must be true. So you read these 3 dots if you haven't seen that before as therefore. This is your conclusion, by the way. Conclusion. And the 3 dots mean therefore. I'll write that a lot. And then some people like to draw a line between the hypotheses and the conclusion just to show that's what we're claiming here. So it's assume this, assume P is true, assume P implies Q is true, then we're trying to prove, therefore we're claiming that based on those hypotheses, Q must be also true. Okay, that's the idea. So that is our argument, and that's the kind of thing we're going to be able to prove. This is a true argument. This is correct. It's a valid argument, we say. So let me show that idea to you in just a second, but let's learn some more terms, of course. There's just a million terms we get to drown in for this lecture. So we say that an argument is valid if the conclusion is true whenever the hypotheses are all true. All right, so assuming both of these, assume this is true and this is true, it must be therefore that Q is also true. So every argument, it really looks like this. You're assuming your hypotheses, H1 and H2, assume that they're all true at once, and they better lead to the conclusion. So all of these better imply the conclusion. So this is really the statement you're trying to prove, all right? So if all the H's are true, then C must also be true. That's what a valid argument is. Otherwise, it's invalid, all right? And so what we're going to learn, what we're going to get really good at in this class is just showing that our argument is valid, because that's what it means to be a proof. All right, that's the definition of proof for us. So that's the beauty of it all. And so it's going to be a lot of symbol pushing at the start, but then we're going to slowly transition to doing it in English instead, once I trust that you're good at the symbol pushing. All right, so here is a good example. Let's use a truth table to prove this, because like we could have proved this with the truth table. Let me prove this one to you with the truth table as well. Here's another argument. So assume this. Assume that the negation of P implies Q is true, and then assume that Q implies P is true. And we're going to prove that, therefore, the negation of Q must always be true, beyond a shadow of a doubt. Isn't that cool? So let's prove this with a truth table. We can just look at the rows, and it'll work out. All right, so the variables involved are P and Q. So let's build truth tables for all these things. And then we'll use that to our advantage in just a second. So what do we got? True, true. So it oscillates true, false, true, false. So this one stays true twice as long. True, true, false, false. That's one way to think about it. And then, all right, let's do this one, let's do this one, and then let's do all these. I'll just do them quickly. All right, Q. Let's do the negation of P implies Q. So what's that? So P implies Q is true in every case. It's like what? You got true everywhere, but here this is just P implies Q. And then the negation is like taking this and negating it. All right, so it's like, all right, this becomes false. This is true. This is false. This is false. So that's that, and I'll erase the scratch work. That's a bit easier, and somehow it's baked in right now. What's going on? Oh, there we go. Weird. All right, back to this. And then let's do Q implies P. So this is the only time this is false is when it's true implies false. All right, you upheld your end of the bargain, but you didn't get the reward. So that one's false, and the rest are true. And then finally we have not Q, because that's the last thing. That's our conclusion. So what's the negation of Q? It's false, true, false, true. And so one way to prove this thing is to look at all the places in the truth table where this is true and this is true, because that's what we're trying to claim. Like under the assumption that this is true and this is true, this better also be true. All right, and let's find that. So where is the negation of P implies Q true? Looks like it's only here. There might be multiple places, but it looks like it's only here. And then where is Q implies P true? Well, they gotta line up. So this is it's true in all these places, but the only time where they line up is here and here. Right? You see how they're both true only there? So this is the row now we care about. So do you see how under the assumption that both of those things are true, that's the only time they are both true, then ta-da, the negation of Q is also true. So this is a correct proof. It's a valid proof. Under these assumptions, it's true. We've proven that beyond a shadow of a doubt. Isn't that glorious? So that is one easy way to do a proof, at least involving symbols. Eventually we're going to get more complicated, but it's your turn. All right, use a truth table to prove this. Assume these two things. These are your hypotheses, P if and only if Q, and then P or Q, and then use that to prove that under the assumption that both of these are true, only in the rows where these are both true at the same time, show that P must also be true. All right. And so I'll do it with you. So again, P and Q are the variables, making it easy on ourselves. So let's try every possibility of those. True, 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 false, false, true, false, false. What do we got? P if and only if Q. Remember that one? That's when they agree. So it's true when they agree. So they agree here and they agree here, but they disagree in the insides there. So it's false there. And then P or Q. Let's see what we got. The only time it's false is when they're both false, right? So this is the only time it's false, but there's a true everywhere else. So it's true, true, true up here. And then I'll just write P over here again just for fun, but I mean it's here already. What is P in all these cases? It was true, true, false, false. And so we're assuming this is true and assuming this is true. So what rows are they both true in? Looks like there's only one. This is true twice, this is true 3 times, but they only overlap here. You see that? So that's the only universe you need to care about. So under these assumptions that they're both true, we're trying to claim that P is also true, and oh man, it sure is. So that is your proof. It's a valid argument because of this. And so you just proved that if you assume this and this, P must be true. Isn't that beautiful? So that is a proof. Not too horrible, I hope. We're definitely going to add to the difficulty, but this is a good start, right? So there's that. Let's next talk about rules of inference, because once you do this, like this is just simple pushing, right? If you have these things, you can conclude that P must be true. If you have these two things, you can conclude that P must be true. Or not Q must be true, sorry. And like there's a bunch of rules, like even this one. If you have these two things, you can conclude that Q must be true. So once you do these once, like it doesn't matter what P and Q are, you can just write them down. So you got rules that you can use to like plop out new facts. All right, and that's where we're going with this, because nobody wants to use truth tables all day long, especially when things get large. All right, so just a bunch of smart people found a bunch of combinations of things that give you new things, new truth facts, and so we're just going to use a table of those for a little while. They're called rules of inference. All right, and so there's a giant table from your textbook. Here it is, and I'll show that to you in a second. But let's look at all these. Some of these are things that we've seen. And we're going to prove one of them, because you just got to prove it once and then you can use it for the rest of time. All right, so like this is called modus ponens. Like logic was big with the Romans, and so this is a bunch of Latin root stuff. So if you have this P and you have P implies Q, like you can plug it into this and like you can get out that Q must have been true, therefore Q. That's modus ponens. Modus tollens is kind of the opposite. If you have P implies Q and you have not Q, then you must have had not P to begin with. It's modus tollens, so this is what the Latin means. And then like if you have P, you can always prove that P or Q is true because you knew that P was true. Like you can add anything. Q could have been any true or false thing. You can add something. If you know that P and Q is true, then both of them must have been true. You can conclude then that P must have been true. And so a lot of these things are kind of like, what's the word? They're kind of common sense, but you can prove them with truth tables, and you never have to worry about them again. But some of these are weird, like this. Like I wouldn't have thought to try both of these and end up with that, but it's useful sometimes. So let's take modus ponens, because that's probably the most important one on this set of slides. You're always going to be using this. Let's prove that this is a correct formula, a valid conclusion, right? A valid proof. So you have P. Assume that, and assume that you have P implies Q is also true. Let's prove that, therefore, Q must also be true, right? So again, we'll set up our truth table, P and Q. True, 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 false, false, true, false, false. And then we got P implies Q, remember that, right? P implies Q. It's only false when you don't have the conclusion, but you do have the hypothesis, so it's true everywhere else. And then again, I'll just write, we're trying to prove Q. I know it's already here. Let me just write it again. So I like it. I like the conclusion to be on the right side. So I'll just rewrite the Q column. So you got all those bad boys, and we're assuming that we're in a universe where both of these are true. We're assuming this is true and assuming this is true. So where's the only time where those are both true? Sometimes there are multiple rows where I'm not trying to say that there's only one time where both of these are always going to be true. It depends on your proof, but it just so happens that P and P implies Q are only true here, right? You see that? It's the only row where they're both true. And so we're trying to claim that Q must be true. Looks like this is the row we're looking at. Is Q also true? It sure is. So, bam, I've got a valid proof. It all works out. So that's the idea. Yeah, so we're going to be using this table a lot to start out, and then eventually some of these will become second nature to us. But again, just like what these are trying to say is like if you have these things, you can always plop out this thing. You have that's true as well. So if we have this, the hypotheses, if we have this, or these, I guess, if we have these, we know that this must also be true, right? We know this is true. Okay, that's what's going on there. And so here's one last example before I let you take a break. So let's use the rules of inference now and the laws of propositional logic, because we got this table, of course, and then we can also like shuffle things around to get it ready for these things as well, because we have, where's the other table? We have this table as well to make things look more like the rules of inference. Okay, so we'll use both of those. And we'll try to make this happen, all right? And this is better, this is gonna not use a truth table, all right? So we're gonna prove that it's valid using these laws, all right? So we're gonna assume that these things are true, these three things, these are our three hypotheses. Boop, boop, and boop. And then we're gonna try to prove that, all right, under those assumptions, not P must be always the case. P must be false, or not P must be true, all right? So let's try to come up with a game plan, because I got these guys, all right? So let's see, what do we have? I need to end up with not P, all right? And I have not R at my disposal, and I got a bunch of implications. All right, so let's look at some of these rules. Did any of these work? Like here we got this one. This might help. We also have a negation. Like some of these things have negations. I like this one. Oh wait, let's see. Dun, dun, dun. Yeah, I kind of like this one because here is the idea. If I have this and I have the negated second thing, the negated conclusion, I can get out that the negation of the hypothesis was true, because I'm kind of like going backwards, using the negation to go backwards. See how that might be helpful? Like I can have this, and then I have the negation of the second thing. That will give me not Q. And then I have this, right? This and not Q, I can use it again to get not P. See how that works? Like I could use this modus tollens twice. Let me write that down. All right, so starting, this is how you do a proof like this. You have like your orders of things. You say like, all right, I'm starting with this. Q implies R, because I want to use both of these in modus tollens, right? Q implies R. I have that. Just like I'm assuming that. So I say I have that by assumption. That's the reason I have this is true. I'm assuming it. Very easy. And then I also, to use modus tollens, I need that not R is true, and I have that also by assumption. Not R is true by assumption. And then to check yourself, let's number these conclusions here. So I'm concluding this is true by assumption, concluding this is true by assumption. I'm just using these rules. And then, all right, now together I can use 1 and 2, right? I can use 1 and 2 and modus tollens to get out that the negation of that hypothesis was true. So the hypothesis was Q here. So I can use and get not Q is true by modus tollens on 1 and 2. So this is how I want you to write your proofs like this on your homework. You gotta give all these reasonings, right, to make sure it's working right. And now I have this, I can plug it into this and also use modus tollens. All right, so I need to get this in my proof right now. So I need to say that, oh, this is true too, because I want to use both of these at the same time, right? And why is this true? Well, it's something that I'm assuming by assumption. It was above the line. So that's 4, and now I can use modus tollens again on these two guys. See, and now it is P and Q again. So that's perfect. It looks exactly right. And I get the negation of the hypothesis out. So I get that not P must be true by modus tollens. Well, let's just make it quicker. Modus tollens on 3 and 4. And I guess if you want to do it in the right order, right, it's, I don't know. I guess it is the negation thing first, and then the thing second. So it is on 3 and 4. So maybe I messed up this one. This is, maybe I should say on 2 and 1 if I wanted to say the order of which I'm using those things to match the table. But it doesn't really matter. I understand what you're going for. And so now I've concluded this from these using rules of inference, and those are all valid things to do. And so this is a valid proof. It checks out that not P is true. All right. So that was some more logic, and I'm sure your brain is hurting right now. So that's where I want to stop for this lecture, and I will see you in the next one. We'll finish up these slides with logic and then start some slides on proofs.